The t-test operates on a very similar principle. Again, we're repeating ourselves in that we have an assumption that there is no difference. With the chi-squared test, it was no difference between the observed and the expected values. But in a t-test, it's no difference between the means of two groups. So we have a group that received supported housing and a group that didn't receive supported housing. And we calculated the average number of hospitalizations in the supported housing group and the average number of hospitalizations in the usual care group. And we see, are these means different? Do they seem, there's going to be differences, right? There's always differences. But are these differences so large that randomness is not a good explanation for the size of those differences? So with the t-test, we calculate the difference between the means, and then based on the assumption of normality, that the means are normally distributed around a point, that difference we found between the mean of the usual care group and the mean of the treatment group, are these differences big enough that we expect to find them by randomness alone? Or are they so big that we wouldn't find these differences except maybe less than 5% of the time by randomness alone? So again, the idea with the t-test is that we have an assumption of no difference between the treatment and control group, and then we look. Are we likely to find a difference of this size by just randomness alone? Well, if the p-value says that 10% of the time we find a difference this big by randomness alone, that's too frequent. We're going to say that randomness is a good explanation for that. We're going to accept the null hypothesis. If it's 20% of the time, we accept the null hypothesis. If it's 30% of the time, we accept the null hypothesis. So we have a very strict standard. We have to get down to finding that difference only 5% of the time. 1 out of 20 times are we going to find a difference this large by randomness alone before we say, maybe randomness isn't the explanation for this. Maybe something else is the explanation. And in our case, if we've done, again, a good job designing a trial where we've isolated just the treatment effect, supported housing versus non-supported versus usual care, then we can say, okay, the difference between these groups is because of supported housing. But it's only if we are not going to find that difference by randomness alone that will make that inference, thus inferential statistics. Let's look at an example of a t-test. What I've shown you on the screen is a set of histograms, 2 histograms, one for female depression scores and one for male depression scores. The females have a mean of 44.85, and you can see that by the black arrow showing you where the mean is on the x-axis, and the males have a mean of 40.81. So there's a difference between those two groups. So men have lower depression scores on average compared with females. Now you can see that there's men that have high depression scores around 60 and women that have low depression scores around 20. So we're just talking about the means of the groups, not individuals in the groups. But we have this mean difference of 4.05, and we want to ask the question, are there difference in depression scores between men and women? So is 4.05 a big difference? Is that a difference that we would expect by random chance? Is this the difference that we're going to get all the time? Remember in the example of flipping the coin, if we flip a coin 10 times, we're not probably going to get 5 heads and 5 tails. We're probably going to get, we might get 5 heads and 5 tails, but we might also get 6 heads and 4 tails, or 3 tails and 7 heads. Those are all things that will happen by just random chance alone. So what we want to ask is 4.05 a difference so big that random chance isn't a good explanation? Or is 4.05 something that we would expect frequently by just random occurrence? And this is exactly what the t-test allows us to ask. Is randomness a good explanation for, in this case, a difference of 4.05? So in order to do that, we use the t-distribution and we map this 4.05 onto the t-distribution. You see the t-distribution here. The red line is the null hypothesis that there is no difference between men and women with respect to their depression scores. That would be an actual 0 difference. This other red line is the cutoff of 0.05, and it has a t-value of 1.66. So if you look at the bottom of the red line where it intersects with the x-axis, you can see that that's right about where 1.66 would be. So if our value, the value of 4.05, when it's converted to a t value, and that conversion is just dividing it essentially by the standard deviation, what we're going to conclude is if it's a 2 or a 3 or over on to the right of that red line, that we are going to say that randomness is not a good explanation. If the t-value is to the left of the red line, we're going to conclude that randomness is a good explanation. Lots of times we're going to find differences that size. So when we convert our actual value of 4.05 to a t-value, it becomes 2.16. So 2.16 is to the right of that red line. So remember, we had the null hypothesis that there is no difference between men and women's depression scores. We are going to reject the null hypothesis because we found that randomness is not a likely explanation. Less than 5% of the time are we going to get a difference of 4.05 by random chance alone. So randomness isn't a good explanation. The alternative hypothesis is that there is a difference between men and women's depression scores, and we are going to accept the alternative hypothesis that there is a relationship between gender and depression scores with respect to this particular sample. Now, correlations are a little bit different than these other tests of association. We can do a statistical test on correlation, again, assuming that the correlation that we're testing against is 0. But generally, what we're looking for with correlations is a magnitude of relationship. So correlations are bound on one end by -1 and on the other end by 1. So correlations have to be between 1 and -1. A correlation tells you the direction of one variable's effect on the direction of the other variable. So for example, and correlations require that both variables be somewhat continuous or countish. There's a variety of different things you can use for dichotomous variables as well, but in general, correlations, we make the assumption that they are continuous or they're count variables. So if we have two continuous variables, like for example, age and the number of hospitalizations. So there's a positive relationship between age and the number of hospitalizations. As you get older, you're going to be more likely to go to the hospital. Hospitals are filled with folks over 65 primarily. So there's a positive relationship between your age and the number of hospitalizations. They're directly correlated. So that number is going to be above 0. It's going to be 0.3 or 0.4 or 0.5. Once you get up to 0.6 or 7 or 8, those are very strong correlations. And once you get to 0.9 or something, basically those are the same variables is what you're saying. But we can do it on the other end too and have negative correlations. So if we stick with age as an example, the older you are, the less likely you are to commit crimes. So the number of crimes committed goes down as somebody gets to be 30, 31, 32, 33, your number of crimes drops. So as age goes up, crime goes down. So there is an inverse correlation between age and crime. And so that number is going to be somewhere in the -2, -3, -4 range. And again, once you get to -1, you're basically dealing with the exact opposite variable. So let's take another look at correlations. Here we have a positive correlation. If you look at the upper left corner, you can see that that's a positive correlation of 0.8. And as you move up on the x-axis, you also move up on the y-axis. So more age equals more hospitalizations. Here is a 0 correlation, where wherever you are on the x-axis does not affect where you are on the y-axis. So these are two variables that are just not related, doing their own independent kind of thing. And finally, we have negative correlations at point -8. So as you move up on the x-axis, you move down on the y-axis. Older people commit less crimes, for example. So this graph over here that we've talked about a number of times this semester introduces this idea that we have a dependent variable that's our outcome of interest, an independent variable that affects that dependent variable, and then a set of other variables that might interfere with the relationship between the independent and the dependent variable. And we've called those control variables or variables we need to adjust for. And I've skipped over this concept of how you do that. How you actually do that in practice and control for these variables is something called multiple regression. And multiple regression uses this idea that there's a slope to a line. You have two continuous variables. Let's just say we have two continuous variables. And there's points along the xy coordinates that you can see on this graph over here. And that we can draw a line through those coordinates that line is calculated using calculus, and it's a minimization function, and it basically says what is the smallest number, the smallest distance between each of the dots and the line. And you can, if you some basic calculus, you can figure out what the line is. Well, that line has a slope. And if there's no relationship between variables, the line will look like this. The slope is 0. If there is a relationship, a positive relationship between the variables, the line will look like that. If there's a negative relationship between the variables, the line will look like that. Now, the difference between these three pictures is one has no slope, one has a negative slope, and one has a positive slope. And borrowing on this concept that we've used all semester, what we're going to say is the slope statistically significantly different from 0? Is the slope so close to 0 that randomness is, we're going to find slopes not exactly 0 by randomness alone 20% of the time? That would be a p-value of 0.2. Or 30% of the time, that would be a p-value of 0.3. Or less than 2% of the time, that would be a p-value less than 0.02. That less than 0.02 suggests that this randomness is not a good explanation for a slope of this magnitude, and so we can conclude that there is a relationship between our x variable and our y variable.
For most of the tables that you're going to look at in the quantitative articles for this class, the most complicated element is going to be the regression table. And regression tables can sometimes be a little bit intimidating, and there are multiple forms. We're just going to go over one, the standard multiple regression form. And what I want to show you is a graphical representation of what those numbers mean and talk you through an example. So what we have here is a regression where I estimated the effect of one's depression score on well-being after controlling for male and female, whether somebody is a male or a female. And so what we're saying is that, okay, so depression score might be related to well-being, but maybe it's really being male or female is related to well-being, and depression scores are related to being male or female, which we found out in our t-test. So I'm concerned that if I try to predict well-being with depression scores, what I'm really predicting is whether being male or female improves well-being and not depression scores. So I need to isolate the effect of depression scores by adjusting my model for male or female. So my null hypothesis in this example is that depression scores do not affect well-being, i.e. the slope for the depression score is really 0, and I'm going to control for gender. So after controlling for gender, there is no relationship between depression scores and well-being. Now, of course, I don't believe the null hypothesis. I believe the alternative hypothesis, or I wouldn't be going to all this trouble to run these models. So I think that there is a relationship between depression and well-being even after controlling for gender, but I'm going to test for my null hypothesis as to whether the slope is actually equal to 0. Now, going back to your high school algebra, the slope is a 1 unit change in x, which produces an whatever coefficient size unit change in y. So if I move 1 unit up on the depression scale from 30 to 31, how much am I going to go up, or it could go down or not move at all, but what is the change in y, well-being in this case? Well, here's the depressions, here's the regression table. And the first line, which says depression scale, and then under coefficient, it's 0.11. So that means that a 1 unit change on the depression scale produces a 0.11 unit change on the y scale, on the well-being scale. And then in the next column, you see the p-value, which is 0.00. So less than 1 out of 100 times am I going to find a value that size by random chance alone, suggesting that randomness is not a good explanation. So we're going to reject the null hypothesis there and accept the alternative hypothesis is that there is a relationship between depression scores and well-being after controlling for gender. Now, that's the coefficient. If you look at the male and female coefficient, what that says is that as you move from female to male, there is going to be a 1.51 increase in the well-being scale. So not only does this regression model control for gender. But it also tells me what the average, in this case, because male and female is a dichotomous or a binary variable, what this is going to tell me is that I move from female to male, my well-being score on average is going to go up 1.51. So, and again, that is also statistically significant at p is probably less than 0.01, suggesting that 1 out of 100 times I'm going to find a difference that big by just random chance alone. So in this case, we found that depression, your depression scale score is related to well-being, and being male is also related to well-being.
I think one of the hardest things in reading papers when you don't have years and years and years of statistical training is trying to figure out what the statistics are. And what I've tried to do in this brief little introduction to these statistical tools is focus on what the tests are actually testing, and not on all of the details behind it, because those are complicated and hopefully will be vetted well by the peer review process. But you should have a set of basic tools now to interpret t-tests, chi-squared tests, correlations, and p-values, particularly as they relate to multiple regression. All of these rest on that central premise of the p-value. And the p-value, as we discussed last week, tells you whether randomness is a good explanation for that magnitude or whether it's not. It doesn't tell you whether it's clinically important. It doesn't tell you whether it's a big finding. It doesn't tell you whether the difference in hospitalizations between my supportive housing group and my usual care group is big enough that we should spend a lot of money on supportive housing. It doesn't tell us any of that. It just tells us, is this difference big enough that we can exclude randomness as the explanation for the size of that difference? That we just sampled and we got a difference, and there's always going to be a difference, and that this difference looks like all the other differences we would expect to get if these things were exactly the same. And so once we conclude that there is actually a difference here that's not just random difference, then we can begin to make inferences and interpret, is that size an important thing? Does cognitive behavioral therapy really reduce depression a lot more, or is it just tinkering at the margins? Does supportive housing reduce the number of hospitalization? Does the MFT intervention reduce the number of child abuse cases? You know, whatever it is that we're looking at, there are two pieces to it. One is the statistical test, which asks whether randomness is the good explanation, and the second is clinical judgment, trying to figure out whether this difference is important. And often those things get confused. People will often say, oh, we found a statistically significant difference, therefore it's important, which is not true. Not true. The magnitude of the difference is not measured by the p-value, except with respect to randomness as the explanation. It doesn't tell you whether supportive housing is worth the huge investment of money, although it probably is. It doesn't tell you whether cognitive behavioral therapy reduces depression more than various forms of psychodynamic therapy. Maybe. It doesn't tell you whether the number of hospitalizations in the assertive community treatment population is enough to justify the expensive assertive community treatment intervention. The p-value tells you none of these things. And so one of the things I hope that you come away from this class with is a sense that there's a bunch of technical stuff here. I can sort of understand what it is. But at the end of the day, understanding whether an intervention produces meaningful difference has to pass over the p-value threshold, but you then also have to ask about it from your own clinical judgment, from your own sense of, are these differences big differences or are they small differences? And that's something that you can do. And I don't want you to get too caught up in the statistics of it, although I'm sure that at this point you are just hungry for more statistical information. But I don't want you to get too caught up in that, and I want you to sort of think over the statistics. Think of this p-value as an initial threshold, but not the final step. And the final step is figuring out whether those differences are important or not. And that's something we're going to discuss in the next section.